This question is about unsaturated aldehydes and alcohols. Part A. 3-methyl-but-2-NL, shown below, is used as food flavouring. 3-methyl-but-2-NL is reacted with hydrogen bromide, forming a mixture of two organic products. One of the organic products forms in a much greater quantity than the other organic product. Part 1. Outline the reaction mechanism for the formation of one of the organic products. Include curly arrows and relevant dipoles. This question is asking about electrophilic addition, so we're going to draw the mechanism for electrophilic addition of 3-methyl-but-2-NL. So if we start by drawing 3-methyl-but-2-NL and hydrogen bromide, we're then going to draw a negative dipole on the bromine and a positive dipole on the hydrogen.
The hydrogen has a delta positive sign as it's less electronegative than bromine. That's why we have a positive dipole on the hydrogen but a negative dipole on the bromine.
There's then going to be a curly arrow from the carbon-carbon double bond or electron density to the hydrogen, and from the hydrogen bromide bond to the bromine. A general rule with curly arrows is 1 in, 1 out. So we can see that there's a curly arrow into the hydrogen and then out of the hydrogen bromide bond to the bromine. Then we're going to form our intermediate. In the intermediate, the carbon-carbon double bond becomes a carbon-carbon single bond. The rest of the compound remains mostly the same, with the addition of a hydrogen. We can either add the hydrogen to the left or right-hand side carbon of the carbon-carbon double bond. Here we're going to add it to the left-hand side, and then the right-hand side carbon becomes positively charged. Then we have our negatively charged bromine, and there's going to be a curly arrow from the centre of the lone pair on the bromine to the positive on the intermediate. It's essential that this curly arrow goes from the middle of the lone pair. Now we're going to form one of our products. We're going to draw our minor product, and that is because we've got a secondary carbocation intermediate. So drawing our minor product, we need to add the bromine onto the carbon where there was previously a positive charge. So this is our minor product. If we were to draw our major product, what would happen is we would have a tertiary carbocation intermediate, and the bromine and the hydrogen would switch places around our compound. So they're on different positions or different carbons in the products. So if we label this major, this is not essential in this question. However, if you do write it, you're showing the examiner you know exactly what the mechanism is, you know exactly why there's a major and a minor product, and it's just going to confirm that you know what you're talking about. To get the marks for this question, you get a mark for having the correct curly arrow from the carbon-carbon double bond to the hydrogen of hydrogen bromide. You get a mark for having the correct dipole on hydrogen bromide, or the correct dipoles, and the curly arrow breaking the hydrogen bromide bond. You get a mark for having the correct carbocation intermediate and the correct curly arrow on the intermediate. And finally, you get your 4th mark for having the correct product, depending on your carbocation intermediate. So here, the correct product is your minor product. Part 2. Explain why one of the organic products forms in a much greater quantity than the other organic product. The reason why one organic product forms in a much greater quantity than the other is something we've slightly touched upon in Part 1. We have a major and a minor product. The statement we need to write is that the reaction goes via the most stable carbocation intermediate, and this is touching upon Markovnikov's rule for electrophilic addition. And our minor product is a secondary carbocation intermediate, and our major is a tertiary. So we can see the higher we go in terms of being primary, secondary or tertiary, the more stable the carbocation intermediate. And this is what we need to write for this question. To get the marks for this question, you get your first mark for saying that the reaction goes via the most stable carbocation intermediate. You get your second mark for then noticing that you have a minor product with a secondary carbocation intermediate and a major product with a tertiary carbocation intermediate. Part B. Geraniol and citronellal, shown below, are isomers present in citronella oil used as insect repellent. Geraniol and citronellal are structural isomers of each other. They also show stereoisomerism. Part 1. Describe how the observations from a chemical test would distinguish between geraniol and citronellal. The test we're going to use in this question is Tollens reagent. Tollens reagent is a test that will distinguish between geraniol and citronellal, and it's a test for an aldehyde functional group. So it's going to produce a silver mirror with citronellal because there is an aldehyde group present in citronellal. Silver mirror is the positive result for Tollens reagent and its test. If we highlight the aldehyde group on citronellal, this just confirms what we already know. Highlighting functional groups is a really good way to then, when you look back at your paper, check your answers and know that you've got them correct. To get the marks for this question, you get a mark for saying Tollens reagent or getting the right chemical test, and a mark for having the correct positive result, so it's a silver mirror with citronellal. Part 2. What is the molecular formula of geraniol? If we start by identifying how many carbon atoms there are, on each peak of our skeletal diagram, I'm drawing a purple dot and this signifies a carbon atom. Then we're going to work out how many hydrogens there are. But firstly, counting the number of carbons, we have 10 carbons present. So do C equals 10. Now using green for our hydrogen. On the carbon atoms as side chains on the end, we would have CH3. So we have 3 hydrogens, which I'm drawing in green. Now, carbon has to have 4 bonds. So on this carbon here, we already have 4 bonds because we have a double bond and 2 single bonds. But on this carbon, we have 3 bonds, so we would have 1 more hydrogen. Here, moving across, we have 2. Again, another 2. On this carbon, we have 4 again. It's a repeat of what we've seen earlier in geraniol. Then we have 1 and 2, and then 1 hydrogen in our OH group. Counting the number of hydrogens, we have 18. So we write H equals 18. That means our molecular formula will be C10H18O, the O coming from the OH group. To get the mark for this question, you must have the correct molecular formula of geraniol. Part 3. Explain why geraniol and citronellal are structural isomers of each other. The question is asking for a definition of a structural isomer. The definition for a structural isomer is that they have the same molecular formula and a different structural formulae. To get the mark for this question, you must write this statement: same molecular formula and different structural formulae. Part 4. Explain the term stereoisomerism. This question is asking us to define a stereoisomer. A stereoisomer has the same structural formula but a different spatial arrangement of atoms. So to get the mark for this question and explaining the term stereoisomerism, we need to write that stereoisomerism is when you have the same structural formula but different spatial arrangement of atoms. Part 5. The structures of geraniol and citronellal are repeated below with the carbon atoms numbered. Explain the types of stereoisomerism shown by geraniol and citronellal. In your answer, refer to the numbered carbon atoms in the structures above and draw diagrams clearly showing any stereoisomers. The first type of stereoisomerism we can talk about is in geraniol, where we have EZ isomerism around carbons number 2 and 3. So in the question, we're shown the E stereoisomer for geranyl. So we need to draw the Z stereoisomer. Drawing the Z isomer, we have most of the compound the same. However, around our carbon 2 and 3 double bond, we would have our group going down rather than going up, so that the highest priority groups are on the same side of the carbon-carbon double bond. So this is our Z isomer. Now we need to talk about the stereoisomers in citronellal. So now looking at the type of stereoisomerism present in citronellal, we have optical isomerism present in citronellal, and that is because we have a chiral carbon on carbon number 3. So we need to draw the two types of optical stereoisomers of citronellal. So now I've redrawn citronellal. I've drawn mirror images of each other because that's what optical isomerism is all about, non-superimposable images. Like your hands, they are mirror images of each other, but they cannot be superimposed. So if we were to show the optical isomerism, we're going to use wedges. So the optical isomerism is around carbon number 3. So we're going to use a solid wedge leading to the aldehyde group on both sides of the mirror image, and then we're going to have a dotted wedge to show our hydrogen, which is one of our different R groups around carbon number 3, which makes it a chiral carbon. A chiral carbon is a carbon with 4 different functional groups attached. So carbon number 3 is a chiral carbon. So here we've now shown the optical isomerism or the stereoisomers of citronellal. To get the 4 marks for this question, you get your first mark for saying that there is EZ isomerism around geranyl and carbons number 2 and 3. You get your second mark for saying that there's optical isomerism and a chiral carbon on carbon number 3 in citronellal. You get your third mark for drawing the correct Z stereoisomer for geranyl, and you get your fourth mark for drawing the correct optical stereoisomers of citronellal. Both 3D structures being correct gets you this fourth and final mark.